Welcome back. So we have been looking at problems and how to solve them by using graph theory and induction and various other proof techniques that we have learned so far. So in this video lecture, we will be looking at this problem that we had discussed a couple of videos ago. So it says that in a football team, there are n teams. Every two teams has played with each other exactly once, and there is no match ended up in a draw. So either of one of the teams must have won. Prove that it is possible to number the teams in such a way that team I beats team I plus 1 for I equals to 1 to n minus 1. Now to solve this problem, we would first like to use graph theory to model this problem, and that would help us to solve it, to visualize the problem. So a quick recap of graph theory. So we have vertices and we have edges, which are pairs of vertices, and this constitute of the graph. The graph is given as the set of vertices and the set of edges. Now there are some basic definitions that are there, and they are, so if u and v is in the edge implies v and u is in the edge. In other words, the relationship is reflexive. We call it an undirected graph. Sometimes weights are assigned to the edges, and in that case it is called a weighted graph. If there is an edge between u to v, we say v is a neighbor of u. And in an undirected graph, the degree of v is the total number of edges that's going out of v. Right? So pictorially, we represent the graphs as these blobs. So here the vertices are A, B, C, D, E, F and G. And we can denote the edges or the relations by lines drawn from one block to the other. So here, for example, this gives us the graph. The edges are drawn between A and D, A and B, B and D, and so on. There is no edge between A and C, which means that A and C are not related in the binary relation. Now there can be edges, weights on the edges, and in that case we call it a weighted undirected graph. And sometimes the edges need not be undirected in the sense that D to A and A to D might be different. In that case we get the directed graph, and we denote it using this arrow. So the arrow says that there is a graph, there is a edge from D to A. This arrow, with the arrow in both sides, it means that there is an edge from A to B and an edge from B to A. Right? So this helps us to represent graphs or binary relations which are not symmetric, which are not reflexive. Okay. Now there are various advantages of using a graph, namely the graphs are very simple objects and they are very simple and very general. So many problems in real life can be designed as graphs in problems in graph theory. So studying the structure of graphs and designing algorithms for graph is an important field. And hence studying graphs in general with various properties can be a way of coming up with a uniform way of attacking various set of problems. So in this video, we will be looking at some more properties of graphs or structure of graphs that we will be studying. So as an introduction to graph theory, there are various properties and structures that keep arising again and again. We have special names for this. We have special names for this kind of structures or properties, and we would like to study them. So here is one of them. It's called a path. So given a graph, a path from U to V is a sequence of vertices V0 to Vk, k can be any number, such that the first one is U, the last one is V, and for all edges, the edge, there must be an edge from Vi to Vi plus 1, or the Vi, Vi plus 1 is an edge in the edge set. So this is called a path. So let's quickly see some examples. So if this is a graph, and I want to see whether there is a path from G to A. So for example, this is a path. So there is a path in the sense that I can go from G to F, from F to D, and from D to A. Right? So in this case, the path that we write is G, F, D, A. So this is V0, this is V1, this is V2, and this is V3. As you can see, V0 equals to G, V3 is A, and there is an edge between V0 and V1, there is an edge between V1 and V2, which is F and D, and there is an edge between V2 and V3, which is D and A. There can be many paths from G to A. For example, this is a path, whereas I can also have this path, G to E, E to B, and B to A is also a path from G to A. So G, E, B, A is a path from G to A. Similarly, say this is another path from G to a much more convoluted path, G, E, C, B, D, A. Now, if the graph is directed, for example, if this is the direction that I have denoted by the arrows, then this is not a path from G to A. Why? Because this edge D to B is going in the opposite direction. Because if I have to go from G to A, then I can go from G to E, E to C, C to B, but I cannot go from B to D because edge is going in the other direction. So one good way of thinking about graphs is as if these are cities and there are roads connecting the cities, and there are roads are one way sometimes. Or maybe you can think of flights. There are flights from G to E, or there is a flight from D to B, but there is no flight from B to D. But when we are asking for a path from G to A, it's basically saying, can I go from the city G to city A by using a sequence of flights? Right? But this is not a valid path from G to A, because I might be able to fly from G to E, I will be able to fly from E to C, I will be able to fly from C to B, but I cannot fly from B to D. This edge is in the opposite direction. But we can come up with another path from G to A, namely this one, and then we get a path from G to A. Now this also helps us defining the next big concept, which is called connectivity. We say U is connected to V if there is a path from U to V. If the graph is directed, it means a directed path from U to V. In an undirected graph, since there is no one-way direction, you can see for yourself that if there is a path from U to V, then there is a path from V to U. And if a graph any two vertices can be reached from one to the another, then we call that graph a connected graph. Okay. So, in other words, the graph is connected if I can go from any vertex to any other vertex, maybe through some direct complicated way. It's something like you have a set of cities in India, and there are flight networks that goes across these cities. Is it possible to go from any city in India to any other city in India using flights? And if it is so, then we call it a connected network or connected graph. Right? So one problem that I would like to assign you is that prove that the relation U is connected to V is an equivalent relation. Okay, so we have looked at equivalent relations in our first week. And this relation, that means U is related to V if U is connected to V. They prove that it is an equivalent relation. Right? So moving on, once you have equivalent relations, it isn't hard to prove from the definitions or from the properties of equivalent relation that the whole graph will be split into equivalent classes. We call them the connected components. So connected component of a graph is the component where any two vertices are connected. And the graph can be written as a disjoint union of connected components. For example, if I have a graph like this, note that the connected component, if this is the whole graph, then the connected components are, this is one connected component, this is the other connected component, and this is the other connected component. There are three connected components here. Right? Good. Now, sometimes we can have paths that end up in itself. So then we call it a cycle. So for example, this is a cycle. A cycle is, I can start from B, I can go to A, D, I go to F, I go to G, go to E, and come back to D. So cycle is a collection of edges that will bring me back to my starting vertex. So that is called a cycle. Okay. In an undirected graph, again, we don't have to worry about the direction of the edges. But when the graph are directed, then we have to worry about it. So this is another cycle that is there, A, B, D, E. But once we put the edges back, we see that this is not exactly a directed cycle. Why? Because I can start with E, go to B, start with E, go to B, so this is fine, B to A, but I cannot go from A to D. Neither can I go in the opposite direction. For example, I cannot start from E and go into D first. So irrespective of which way I go, I cannot come back to my place following this set of edges. So this is not a cycle. But this one is a cycle, directed cycle. Why? I can go from G to F, F to E, and E to G, because E to G exist. So this is a directed cycle. Right? So if a directed graph does not have a cycle, we call it an acyclic graph. And if in a connected undirected graph that has no cycle, we call it a tree. Now, this is a very important concept. We will come back to this concept again and again in this next few videos. Trees are very important objects. They are undirected acyclic graphs or undirected graphs that don't have a cycle. For example, here in this graph, this is a tree. The set of red edges forms a tree. Note that by looking at the red edges, if the red edges were only part of the graph, then there wasn't any cycle. So red edges don't form a cycle at all. So this is a tree. We can have many trees. For example, this is another tree. Right? So I mean that the red edges are the tree edges. So connected undirected graph that doesn't have a cycle is called a tree. A tree that touches every vertex is called a spanning tree. Just like in this case. If the original graph is this whole graph, and if red edges forms a tree, note that it touches every vertex in this graph. So this is a spanning tree. Now there are a few problems that I would like you guys to think about. We'll come back again next week to solve many of the problems. First of all, how many edges are there in a tree on n vertices? Can you give me a number? And secondly, just like we have been talking about the spanning tree or the example, if G is a graph and H is another graph, we call H is a subgraph of G if the vertex set is a subset of the original vertex set and the edges set H set in H is a subset of the H set in G. Or in other words, if I give you a G and if I remove some of the edges, then I get a subgraph of G. A question is that does every graph has a spanning tree as a subgraph? Okay. So this kind of the quick introduction to graph theory. And now using this set of graphs that we have learned or various graph theory that we have seen, can we at least formalize this statement of this problem? So here again, there are n teams. Any two teams play with each other. One of them wins, the other one loses. Prove that it is possible to number the teams in such a way that the team I defeats team I plus 1. So to formalize it as a graph theory problem, we have to first set up a graph. So of course, let there be n teams. Sorry, this is not n, this should be just not 2n but just n. There are n teams, so let the n vertices be v1 to vn. And we draw an edge from vi to vj if vi defeated vj. The team vi defeated team vj. Since vi defeated vj does not imply vj defeated vi. So in fact the graph is directed. So here it is not an undirected graph but we have a directed graph. And moreover, between any two pairs, since they have played with each other, Vi and Vj, there must be an edge and there must be exactly one edge, meaning there is an edge either to Vi to Vj or an edge from Vj to Vi, not both. Such a graph is called a tournament. A tournament is a graph where between any two vertices there is an edge, but the edge is oriented, or in other words, the edge is either in one direction or the other, not in both. The question is that, is there a path where every vertex appears exactly once? Now, why is it the right question? Let me quickly, before I define the Hamiltonian path, let me quickly try to understand, give an example of it. So say I have the teams, okay? So here are 4 teams, A, B, C, D. And say A has defeated B, but C has defeated A, B has defeated C, D has defeated C, but D has been defeated by A and B has been defeated by D. So this is an arbitrary graph of a tournament. Now what do I mean by what do I have to do? I have to order them in such a way that the I team defeats the I plus 1 team. Now in this particular graph, think of this way, that if I number D to be equals to 1, B to be number 2, C to be number 3 and A to be number 4, what do I have? I get D, B, C, A, and note that D defeated B because of the age, B defeated C because of the age again, and C defeated A. So I get a path here like this, where every edge, every vertex is coming once. So this is what I have to get. So I have to get a path like this which touches every vertex exactly once. So this such kind of a edge or vertex, such kind of a path is called a Hamiltonian path. Going back to the problem, so our formulation seems to be right in the sense that what we have been asked to do is find a path where every vertex appears exactly once. So such a graph, such a path is called a Hamiltonian path. A graph in general may or may not have a Hamiltonian path. And it may or may not have and if there is a cycle of that form which touches every vertex exactly once, we call it as a Hamiltonian cycle. So graph may or may not have a Hamiltonian cycle also. So let's look at some of the examples. So if this is a graph, now let's try to see whether this graph has a Hamiltonian path. How about this one? Now this is a path which is a proper path because I can go from E to G, from G to F, F to D, D to B and B to A, but I cannot extend it to go to C. In fact, you can convince yourself that this particular graph does not have a Hamiltonian path. But if I had flipped this edge E to C and made it into a two-way path, then I could have got a Hamiltonian path of this kind. C to E, E to G, G to F, F to D, D to B, B to A. So this gives us a Hamiltonian path. Note that this graph does not have a Hamiltonian cycle. Also, note that this graph is not a tournament because there is no edge between A and C, either this way or that way, and so on. I don't have an edge between A and E also. So the problem, so in a general graph, we can have a Hamiltonian path, need not have a Hamiltonian path. But the problem now states that if G is a tournament, that means between any pair of vertices there is an edge going from U to V or V to U, proves that there is an Hamiltonian path. So you have to prove that a tournament has a Hamiltonian path. And this is the formulation of the problem that we have in terms of graph theory. Now, how to prove it? Again, the hint is induction. We will come back next video and prove this problem using induction. We have now converted the problem into a problem in graph theory. So in the next class, we will use induction to prove that every tournament has a Hamiltonian path. Thank you.